Okay, we are now recording. Let's hit a couple of just housekeeping issues first, and then we'll we'll get on into um, the last that we'll cover today. This is the day you've been dreading all term, the last day of class, okay? But it's here, nothing we can do about it, it's here. So what we're going to do now, I know that I can't keep it straight in my head who's done what. I think that maybe both of you have turned in your research papers. If you haven't, please get those in. Oh, here comes Aaliyah. Let me get her in here. All right, 3 out of 4. This is good. All at the bottom of the alphabet, we're waiting on Ricky. However, Ricky wasn't there at the first class. I know she has a whole lot on her plate right now, so she may not make it today. Hope she will, but she didn't make it the first class. So we've already started recording. Aaliyah, what I was talking about is how we're going to wrap things up. I think I went through this last time, but just so everyone hears it and it's all fresh. I'll first give my sad song here. I printed just about all day yesterday that I wasn't in class, which wasn't much, but some. This is what I've printed since the weekend, okay? It's enormous, okay? And I know I've got more out there. I got everything printed that was printable yesterday afternoon, but I know that other stuff has come in this morning. Maybe not a lot, but some. Because I gave several things out yesterday to both of my classes then, so I know some of that has already started coming in. And if it hasn't, it will. So basically, the rest of my week and weekend pretty much is going to be spent grading papers. Every now and then I'll have to print some more papers to grade, but it's grading papers. Once I get them graded, then I've got to enter everything on Blackboard. So that's going to be a huge part of the weekend. So therefore, here's what my plea and my begging is going to be. If you haven't submitted your research paper yet, please get it in. And I think maybe all of you have. I don't have them all graded, but I know 2 of the 3 had submitted them. I've already graded. The other 2 I may have in my stack. I just haven't checked this morning to see. I've been printing paper so much I can't keep up with who's what. Okay, so and both Aaliyah and Jemanuel are in 2 different classes, and I can't remember who's turned in what for which class. So I should know, but I don't. If you don't have your first test in, please get that one in. If you don't have the second test in, please get that one in. And if you don't have the third test in, I need those. I need them so I can add them to the stack to grade. I've got to have those because I want your weekend or the rest of the week and weekend free to finish this last test. So if you haven't finished the others, get those to me just as soon as you possibly can. Okay? Then, because at the end of the class today, in fact it's already out there, is your 4th test. And we'll talk about the last 5 minutes. I talked about this with James before Jemanuel and Leah got here. Stop me 5 minutes before the end of class so I can go over that test with you. I've got it out here. I hope that I'll be able to pull it up in this. I opened it before class. Hopefully I'll be able to pull it up. Now, if you can get anything you don't have turned in now, get it to me as soon as possible, preferably today. Okay, you have this afternoon. I don't know, you may have other classes and stuff. Get me everything you can today of the old stuff. Research paper, test 1, 2, and 3. Please. And if you can't get it to me today, get it to me as early as you can tomorrow. Don't sit and wait, well, I'll turn it all in at the same time. No, please don't do that. Get it to me as you finish it so I can, if I am printing, I can go on and get it printed. And if I am grading, I will be grading. I can go on and get working on grading it. Okay, now the thing I'm giving you today, the test, I'd love it if you could finish that this afternoon too. I know some of you can't. You may have plenty of other stuff on your plate. Okay, tomorrow would be fantastic. Okay, Saturday will be okay. Get it to me Saturday. I may not have as much opportunity to print and grade on Saturday as I will tomorrow, but that'll be fine. And then if not, I've got to have it Sunday. I'd love it by midday or no later than mid-afternoon on Sunday. Because if you send it to me Sunday night, there's a real good chance I won't even see it until I get the grades in. Because I'm going to be grading the stack of papers. I'm going to be entering grades on Blackboard. I'm going to be computing averages. I'm going to be entering grades on the system. And at some point, I won't have time to go back and look at emails or at Blackboard messages. If it comes in late Sunday night, there's a real good chance I won't see it until I've turned in grades on Monday. You'll get an incomplete, and then I'll go back and check everything, because I usually send messages and emails to all the students I've given incompletes, and then I'll find it there, and then I'll grade it and then change your incomplete to a letter grade. I'd rather not have to go through that. Excuse me, I've got to sneeze. I tried to move the microphone in time. I hope I didn't blow y'all out. Okay. So any questions on that? The point being, get me as much as you can as soon as you can. And if you wind up with an incomplete, that's because something came in so late I didn't even see it. Okay. And sometimes, I guess, Leah, I think you're a prime example of that. I sent the invite for Zoom for what? The last class, my Cal 3, Cal 2 class, and you got it hours later, okay? Okay, so if that's happening your way, because I sent that thing probably no later than 6 o'clock or 7 o'clock that night, and you didn't get it until after midnight or something, it seems like. I don't know why it takes so long. If you send me something 6 o'clock Sunday afternoon, it may not even get to me until 11 or 12. I'm going to be asleep by then. I hope to be asleep by then. So get me something as early as you can, as much as you can, as early as you can. All right, any questions on that? I've harped on that too long, probably. Okay. If not, let's go on and get started with linear algebra. Okay, any questions on that either? Okay, we're in chapter 4, vector spaces. The section we're in is 4.4, and the name of that section is spanning sets and linear independence. Now, we just got going on this and got a pretty good start on it last time. Where we are now, excuse me, is on page 178, just about the bottom half of the page, theorem 4.7. We talked about what the definition of a spanning set was, the span of a set was, okay? And I usually call them spanning sets, but they call them the span of a set. And basically what it means is this. If you have a set there, has all these different things in it. If you have a number of vectors, now remember, a vector can be a matrix, an equation, a function, polynomial, it can be all sorts of things. If you have a series of those, that some linear combination of those few, 2, 3, 4, whatever of them, covers everything else in that set, then we say you've spanned the set. You have the span of the set. So here is theorem 4.7. Okay, I think what I'll do now is go to the whiteboard. Now, do all three of you have your books today or not? Everybody got a book? Okay, I heard James has one. Emmanuel, you got one in front of you? I can't hear you. Aaliyah, you got one in front of you? It's okay if you don't. I'm just asking. Okay, I can't hear any. Okay. And Jemanuel, do you have a book? Still can't hear Jemanuel. Okay. So I'll assume that maybe he does it in front of him. He did not. Okay, thank you. I saw that there was a chat out there, but I hadn't had a chance to open it. I was trying to arrange my whiteboard so I can have maximum writing space on it. So he said no, he did not. Okay, yes, he said no, right? Okay. Okay, got it. Okay. So let me go on and write this out then. I was wondering. Oh, here's Ricky. Excellent. Perfect attendance the last day of class. I think this is by far the best attending class I've had all term. I've had perfect attendance so many days with you guys. I really appreciate it. Okay. Now, Ricky, we're in Chapter 4, Vector Spaces, Section 4.4, Spanning Sets and Linear Independence. And let's see, 2 people have entered the waiting room. Oh, that's Ricky and Ricky. So Ricky hasn't heard a word I said. She must be having trouble getting in. I know one person this morning, when he came into the class, it took him forever to get audio. And Ricky's trying to do that right now. I guess she's got it. Okay, she's here. Okay, so I'm going to can this. All right, welcome, Ricky. We're in Chapter 4, Vector Spaces, Section 4.4, Spanning Sets and Linear Independence, and we're just about to do on page 178, Theorem 4.7, which talks about the span of a set. Okay, now just to fill you in on what we talked about earlier, since everybody's here, way to go. Let me just go this quickly. If you have not gotten me a research paper, get it to me as soon as is humanly possible. If you haven't turned in the first, second, or third test, I need those just as soon as you can get them sent to me. So if you're still working on more than one of them, as soon as you finish one of those things, send it to me. Then get working on the next one. I want them as soon as I can get them. Don't wait and let them pile up and send them all to me at once. That really messes my ability to get things graded as efficiently as possible. And already I'm not very efficient with the grading because basically since the weekend I've received that many papers. I'm teaching 5 classes. 2 of them are very big classes. The other 3 are smaller classes. Only one is as small as this one. The other one's sort of a medium size. So I've been getting tons and tons and tons of back work coming in. So I'm going to be grading like crazy this weekend. So get me the stuff as soon as you can. And as I was saying before, I've already posted out there the last test, this Chapter 4 test. I posted it on Blackboard message this morning. And once you get the other things caught up and sent to me, get working on that and get me that one as soon as possible too. But here's what I was saying. I would love to have anything turned in that could be turned in today, if at all possible. If you can't get everything in today, get me as much as you can today, and then get me as much else as you can tomorrow. Okay? Saturday, I'm going to be out of pocket for a little bit of time, but get me stuff on Saturday, because when I get back in pocket, then I'll be copying things, printing things and stuff like this. So don't hold off and say, oh, he's out of town. No, just wait and send it to. No, get it to me, because when I get back, I will be printing. Okay? And when I'm printing, I'll be grading. Okay? Now, If you can't get everything to me by Saturday, if you get it to me Sunday, and this is what I've been telling all my classes, if I receive it after, I don't know whether to say midday or mid-afternoon on Sunday, if I receive it after that, there's a good chance I'm not even going to see it, because I'm going to be grading and grading and grading and grading. At some point, I'm not looking at emails anymore. I'm not looking at Blackboard messages anymore. I'm grading to try to get all the grading caught up. And then once I finish grading, I'm entering things on Blackboard. And once I get it entered on Blackboard, I'm recording it in my grade book and putting the grades out there on for submission. So at some point, and we were talking about this before with Aaliyah's example, I sent something on, I think, Blackboard message that other people got, but she didn't get until hours later. Okay, and there's no rhyme or reason why that happens, but it does happen. So if you send me something at 4 o'clock on Sunday afternoon, it may not show up on my email or Blackboard until 10 or 11 o'clock that night. And guess what? I'll be in bed. Okay, I'll be hopefully sound asleep by then. I will not see it until maybe Monday morning, and Monday morning I've got to get grades in. I cannot be fiddling around with printing and grading papers when I need to be entering grades. So please, folks, get me things as early as you can, as much as you can, as soon as you can, and keep it coming. All right, we were, like I said, page 178. Yes. Excellent. That is such good news to hear. If everyone could do that, then that really gives me a lot more flexibility. I'm going to be grading like crazy anyway, but the sooner I can get it, the better. So thank you for that. So here, middle of page 178, theorem 4.7. If you have a set S, and this set S consists of a bunch of vectors, V1, V2, V3. If I write too fast, the pen doesn't work well. I don't know why that's the case, but I have to do it slowly. If I don't do it slowly, it screws up. All the way up to and including V sub k. Now, if you were present for the earlier classes in this chapter, you'll realize these vectors don't have to be directed line segments anymore. They could be polynomials, they could be functions, they could be matrices, they could be just about anything, okay, that fits the bill, okay. Anything that follows a vector addition principle and a scalar multiplication principle. Anything that follows that, they could be. So this is a set of vectors in a vector space, and VS stands for vector space, and that vector space is capital V. Then, what we call the span of that set S, the span of S, this drives me nuts, the span of S is a subspace, and SS stands for subspace, of V, of the vector space V. Okay. So it's not just another set, it's actually a subspace of V. Moreover, there's kind of point 1, okay? Moreover, the span of S, and I'm intentionally writing in lowercase, span of S, is the smallest, and there, if I write too fast, it doesn't write well. So if you think I'm writing slowly, it's because if I don't, the pen screws up. The smallest subspace of V that contains S. I wrote too fast and it didn't write. Yuck. That contains that set. In a sense, this is sort of wordy. In the sense that every other subspace of V that contains S there. I write too fast and it won't write. That set S must contain the span of S. Now that's a lot of blah blah blah, okay? Now what this means, here's a set of vectors, okay? These vectors are all, this set of vectors is all in this space, vector space V. Now, the span of S does not mean all these vectors. The span of S is really the smallest number of those vectors, and this is what we talked about before, that you can have, that some linear combination of those vectors will make up every other vector that's in S. Every one of them, okay? It's the smallest collection of those vectors V that will, by using them as a linear combination, you can make all the other vectors. That's what the span is, okay? Lose one of those, you can't make that whole set anymore, okay? You need every one of them. So that span of S is a subspace now of V. It's not just a subset, okay? It's a subspace of V. That span of S is the smallest subspace of V that contains all those vectors S, okay? Because that's why we chose it, the smallest number of them that you can make happen. In the sense that every other subspace of V that does contain S must also contain that span of S. All right, sort of running around in circles there, but that's what we've got. Now, top of page 179. We're talking here about linear dependence and linear independence. And we've talked about this before in other contexts, so let's make sure we get a good understanding here. For a set of vectors, okay, I'm going to go to a new slide. Does anyone need that one any longer? Okay, that was mostly verbiage. This is actually a bit more practical, I hope. Okay, here we have a set of vectors S, same as before. That's why I wanted to get this, and we're naming it the same as before. These are vectors V1, V2, V3, and so on, and so on, and so on, up to and including V sub k. That is set S. And that is in the vector space V. This is starting just like before. If I can get my pen the pen will not pick up. Okay, quit. I don't know what that's doing. Okay, already did this once and doing it again here. This is in a vector space. Starts off just like before, capital V. Okay, now for that set of vector, here is a vector equation. Let me see if I can write it all on this line. This is so aggravating. Okay, C1 V1 plus C2 V2 I don't know why this thing is in the way. Okay, I don't know how to run this well, so that's part of the problem. Plus C3 V3, and that was supposed to have an arrow over it, but it didn't write. Plus dot 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 plus C sub k V sub k. So this, okay. Now that's the zero vector because it's a sum of other vectors. That vector equation always, absolutely always has a solution. Okay? And the obvious solution would be that C1 equal C2 equal C3 equal dot 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 equal C sub k, and every one of them is equal to 0. The number 0, because C's are scalars, the linear combination is a vector. Alright, so obviously there is a set of C's that will make that true. Okay? However, what if that's true when all the C's are not equal to 0? There's at least a few of those C's out there that are not equal to 0. Now, if that's the case, and those are called non-trivial solutions. This is called the trivial solution. And let's just go back to a case we did. Example 1a. Here was your S then. And these were actual vectors in 3 space. The first one was 1, 3, 1. Remember that one? I said that was a zone defense we used to run in basketball. 0, 1, 0. 1, 0, negative 5. Okay, there was a set, simple set, 3 vectors in 3 space. Now it may have been that those were linearly independent. If they were, that would be a span of R3. Now we haven't gotten there yet, but it would be. But if these aren't linearly independent, then that means this does not span R3. Okay, and we saw before that if you do three times the second vector there, that won't work. Minus 4 there 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 is a set. I'm not going. You can go back and look at the problem again. Call this vector 1, vector 2, and vector 3. Seems like there was a pretty easy way to see that, and I'm not seeing it right now. That V1 can be written as a linear combination of the other two. It was 3 times V2, that's what I was saying before, plus V3. But when I was doing that in my head, that doesn't seem to work. Well, the reason it doesn't work is that I wrote it wrong. Okay, duh. Yeah, that's a 0, 1, 2. Because I was going to say that is not true. And it's not true because I wrote the wrong thing. 0, 1, 2. Now, okay, that will work. 3 times vector 2 plus plus vector 3 will give you vector 1. So therefore, these 3 vectors do not span R3 because one of these is a linear combination of the other two, so it's not going to span the whole set. Okay. Now, there you have C1, C2, and C3 that are not all 0, and yet that would produce a 0 vector. Okay. The other way of saying that is if C1 was 1, so 1 times 1, I can't write too fast, 3, 1, minus 3 times 0, 1, 2, okay, and I believe it's minus 1 times 1, 0, negative 5 is going to equal the 0 vector. And not all of those C's, in fact none of the C's are 0. 1, negative 3, and 1. So this is not the other way of saying this is not a set of linearly independent vectors. One of them depends on the other two. Okay. When a non-trivial solution exists, like it did here, it gives you the 0 vector without having all zeros as your constants, then the set S is linearly, I have to write slowly, dependent. In other words, at least one of those vectors depends on the other two. Okay? Had the only solution been the trivial set where all the C's were equal to 0, and that's the only way you could get a 0 vector out of it, then we say it's linearly independent. Okay? If all C's have to be 0, for that equation to hold, then the set is linearly independent. Okay. I left off with independent. Okay. Independent. Okay. That concept is essential in the study of linear algebra. Linear independence, linear dependence. Okay. So here's the definition that goes with that. And this is one of those long wordy definitions. Okay, a set of vectors, S, and it's just like we've had before. V1, V2, V3, comma, dot, 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 comma, V sub k. And remember, that can be any kind of a vector too. In a vector space, is, this is just saying what we just said before slightly differently, linearly get out of there. I don't know if y'all can see that, but it messes up my screen and I can't write. Linearly independent, I'll write that down here, so if I write cursively you can't read it, but it writes better. Okay, when the vector equation C1 V1 plus C2 V2 plus C3 V3 plus dot 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 plus C sub k V sub k equals 0 equal the 0 vector has only to deliver the trivial solution. I don't like writing cursively, but it works better with this pen for some reason. Trivial solution. What we mean by that, the trivial solution, C1 equals C2 equals C3 equals dot 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 equal C sub k, and they're all equal to the scalar number 0. If there are also non-trivial solutions, if that's the case, and in fact you can find some c's other than 0 that makes that vector equation true, then S is linearly dependent. Sorry, I'm going to have to write cursively. All right, so there's our definition. Anyone need that up a little longer? Okay. Here's example 7. Here's a set, S. Boy, we've seen that before, haven't we? Favorite name for a set is S. Favorite name for a vector space is V. Favorite name for a function is F. I mean, mathematicians are very creative, aren't they? Here is a set of ordered pairs, 1, 2, 2, 4. Okay, this set is certainly in R2, set of all ordered pairs. What you reckon? Is that linearly dependent or independent? Exactly. So therefore, -2 times the first one plus the second one is going to equal 0. And those two constants, -2 and 1, are not 0. Okay, so this is linearly, come on pen, get back here, is, I have to write it out, linearly independent, dependent, sorry. Yeah, quit that. Independent means the only way you can get the sum of those vectors to equal, some linear combination of those vectors to equal 0 is if every coefficient is 0. All the c's are 0. Otherwise, there's no way you can get that to be a vector equation equaling the 0 vector. Okay? That's what it means. If you can find any constants you can put in there that are not 0 and makes the equation equal 0, that's dependent. If you can't find any, that's linearly independent. So here's the B part. Here's a set, 1, 0, 0, 1, -2, 5. Okay, these are certainly all in R2. They're all ordered pairs. Okay, is that linearly dependent or independent? It's linearly dependent because -2 times this plus 5 times that is going to produce exactly that vector. Let me give you a hint. Now this goes for our regular old vector spaces. If it's R2, you cannot have a collection of vectors more than 2 that are going to be independent. Because guess what? Your spanning set is going to consist of 2 vectors. The smallest number of vectors that can include every other vector will be 2. So as soon as you see 3 vectors in a R2 vector space, not independent. They are dependent. Okay? Yep, -2 times 1, 0 plus 5 times 0, 1. You're going to get, okay, and then just add -2, 5. That's going to give you the 0 vector. And those coefficients, -2, 5, and 1, none of them are 0, okay, much less all of them being 0. Now if you didn't include this vector in there, sure enough, there's no way you're going to get one of these as a linear combination of the other one. Just not going to happen. Those are your standard spanning vectors for R2. 1, 0, and 0, 1. That will cover everything in R2. Okay, how about number C? Here's a set. S, favorite name for a set. 0, 0, 1, 2. And certainly those 2 vectors are elements of R2. They're both ordered pairs. Now, is that linearly dependent or independent? Okay. Give me a number. Make up a number as big as you want it to be? Give me a number. Huh? 6. 6 times 0, 0 plus 0 times 1, 2. What does that give you? That gives you the 0 vector. You're absolutely right. And these two coefficients are not 0. 6 is not 0. The second one is 0. That's fine. But the first one's not. And remember, every coefficient has to be 0 if it's going to be a... Say again? No, no, no. They all have to be 0. Yeah, they all have to be for it to be linearly independent. This one is not. Okay, now, here's another hint. If you have the 0 vector in your set, it is not independent. Okay, we've just shown it. Okay, so this is linearly dependent. All right, good deal. Any questions on that? Good questions so far. Ask them if you got them. Okay. Now, let's move to example 8, top of page 180. And even if you don't have a book on you, or even near you or around you, but you do have a computer, guess what? You can go to larsonlinearalgebra.com for an interactive version of this type of example, example 8. Let's determine whether the set of vectors in R3 is linearly independent or dependent. So here's your set. Our favorite name for it, S, is a set of these 3 vectors here. We're going to name them V1, very cleverly named vectors. V, favorite name for a vector is V. V2, cleverly disguised, and V3. Okay. And that set of vectors is one, two, three. My dog just left me. She was upstairs sleeping, but I guess I'm making too much noise, so she went downstairs. It's probably too hot up here too for her. So 0, 1, 2. Have we seen these before? Please say yes. -2, 0, 1. Determine whether that set of vectors in R3, and these are all vectors in R3, is linearly independent or dependent. What you think? You say independent? Okay. Don't you remember these 3 before? That vector 1. Oh wait, did I write that right? Oh, okay, sorry about that. I thought this was our favorite set from before because they started off the same. Remember the first one we did? Where is it? No, that was our 1, 3, 1. Okay, sorry. Okay, I don't know this one. Okay. All right. Why do you say independent? Okay, you're coming in very, very softly. Can you? Okay, I don't write off the top either. So what we do, we test it. Okay, And this I think we have done before in an earlier, last time. I was thinking it was this time. Let's do a C1 times the first one. 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times -2, 0, 1. Okay, and let's set that equal to 0, 0, 0. And let's see if we can come up with those coefficients. Okay, now let's write down the equation. That would be C1 plus C2. No, that's a 0. I can't read my writing here. Let's see if my eraser will still work. It quit working in my first class, but it came back now. Okay. -2. Yeah, I should have erased that too. Let's just block that out. -2 C3 equals 0. 2 C1 plus C2 plus C3 equals, say again? Oh, you're right. Okay, let me do that a little bit neater. Oh, no, there it comes. Okay, sorry about that. You're right. I was looking at the third one. 3 C1 plus 2 C2 plus C3 is equal to 0. Well, what would we do to solve a system of 3 equations, 3 unknowns? Gauss-Jordan elimination. You set it up as a matrix. Absolutely right. And that's going to be 1, 0, -2, 2, 1, 0, and 3, 2, 1. Now I could put the zeros here, but they're never going to change. So basically all we have to do is find out if this is an invertible matrix. Can you come up with the identity matrix from this when you do Gauss-Jordan elimination? Now I do want to point something else out to you. Notice what these columns are here. These columns are the elements of the vectors. Vector 1, vector 2, vector 3, column 1, column 2, column 3. So we don't have to write that equation anymore if you can do that. So let's do our Gauss-Jordan elimination. So we'll do -2 times row 1, I was going to say vector 1, which is row 1, plus row 2. So that's going to produce this stays the same, 1, 0, -2. This one becomes 0, right? -2 times 1 is negative, okay. 1, and isn't it +4? I know my minus sign didn't show up well. Okay. Don't pay attention to me, James. You should know better than that by now, okay? This will be a -3 row 1 plus row 3. Okay, things aren't writing well. That would be a 0. That would be a 2. And that would be a, say again? 7. Okay, I couldn't hear my ears are really bad. All right. Now let's do a quick review. We got a leading one here, zeros below it. Hey, we happen to have a leading one there and also a zero above it. We just need a zero below it. So we're going to do minus 2 times row 2 plus row 3, and that will produce, I'll come over here and write 1, 0, negative 2, 0, 1, 4, and this will be a 0, that will be a 0, and that will be a isn't a negative 1? Is it? Negative 2 times 4. I'm sorry. Oh, you did say negative 1. Okay. You're right. Okay, I thought you said 1. Okay. Now, but the next thing I'm going to do is multiply that last row by minus 1. So now it is a 1. Okay. And guess what? I think you can see this will turn up, because remember, any matrix that is upper triangular is invertible. Remember that? Or lower triangle is invertible, because the rest of it is just, 2 times row 3 add to this one, that'll work. Negative 4 times row 3 add to row 2, that'll work. Yes. Okay. So therefore the only, and remember, if we had put our fourth column here, that would have been 0, 0, 0, everything we would have done, we kept it 0, 0, 0. Then you get C1 equals 0, C2 equals 0, C3 equals 0. There aren't any parametric equations. There's no other choices that will work. Okay, so therefore this is, you're right when you said it, linearly independent. Okay. Now, do you begin to see the connection between what we've been doing, Gauss-Jordan elimination, and finding linear independence or dependence? In other words, if this was an invertible matrix, and remember, lots of things you could have checked. Gauss-Jordan is about the easiest, but you could have also, just done a Gauss elimination. That would give you upper triangular like we got. As soon as you see that, you know you're good. Okay? Or we could have done the matrix, the determinant of the matrix. If that was not 0, it's good. Linearly independent. Okay? Now they went through in gory detail. I just left off that last row of zeros because it's never going to change any. Okay? Linearly independent. Now, James's eyes were good. He said, I don't see anything that'll work, and you happen to be right. But this was maybe a little more reliable than James's eyes, but maybe not. Okay, we won't say that. All right. So let's look at the testing for linear independence and linear dependence. Basically, it's going to do what we just did, so I'd just as soon not write this unless one of you says, no, I really need to see this written. Okay? Let S be your set of vectors. K vectors there. Be a set of vectors in the vector space V. Okay? To determine whether S is linearly independent or dependent, here are the steps. From the vector equation, C1 V1 plus C2 V2 plus V3 V3 plus ... all the way up to C sub K V sub K, set that equal to the 0 vector. In other words, if this was whatever space you're in, make that the 0 vector in that space. Write a system of linear equations in the variables C1 through CK. Okay? What were your coefficients have now become your variables. Okay? Determine whether the system has a unique solution. And if you remember back, there's like 6 different things that can determine that. Gauss-Jordan elimination, Gauss elimination, determinant. It seemed like there were some others. Okay? But any of those, if you can determine that is that set of equations does not have any solution other than the trivial solution, you got it. Okay? See if it has a unique solution. If the system has only the trivial solution, then the set S is linearly independent. If the system is not, also has a non-trivial solution, at least one, any one, then it's linearly dependent. All right. Now, they have a little blurb at the bottom of the page that frankly to me looks almost grotesque. Okay, excuse me just a minute. But it's something that's used a lot these days, maybe used too much these days. It's what they call image morphing. Okay, this would be something like, I don't know if y'all remember, y'all are probably too young to remember, there were some movies that dealt with avatars, and I've never saw one of them, but it was my impression that a human morphed into something else. You know, it was transformed into something else. And you see this happening sometimes. It's all science fiction type stuff, but it sells. Okay, so image morphing, guess what? Uses linear algebra to do it. Okay, surprise, surprise. So let's move on to example 9. Testing for linear independence. All right, I'll tell you, just too many moving parts here. This desk is too small to hold everything I need. So here is to determine whether a set of vectors in P2, which is polynomial space, all polynomials of degree 2 or less. Let's see if it's linearly independent or linearly dependent. So here's now your set, favorite name S. It is a set, but this set is going to contain polynomials, not your traditional ordered set of numbers. Okay, the first one is 1 plus x minus 2x squared. The second one is 2 plus 5s x. Sorry, where did the s come from? My word. Oh, I guess it was on the outside. Okay. Brains do strange things sometimes. 2 plus 5x minus x squared, comma, third one is x plus x squared. Okay. Now, they do right above this, call this one vector 1. Again, calling it a vector even though it's not a traditional vector. That's vector 2, and this is vector 3. Now my lines aren't drawing here. I don't know why. Okay, that one finally did. Okay, I'm up into the blue space, so that doesn't do well. Okay. Now, we test them just the same as before. We say, is there a set of C's, C1 times the first vector, 1 plus x minus 2x squared. Now, James, you better have checked to make sure I have all my signs and exponents right. plus C2 times the second vector, which is 2 plus 5x minus x squared plus C3 times, I think that's just x plus x squared. My V3 was throwing me off there. I think that's just x plus x squared. Is that equal to 0? In other words, 0 plus 0x plus 0x squared. Let's just write that as the 0 vector in P2 space. Okay, so let's multiply through and see what we get. We get C1 plus C2, I'm just doing the units now, I'm sorry, plus 2C2 is equal to 0. The constants have to be 0. Then we have a C1 plus 5C2 plus C3 This aggravates me. Plus C3 is equal to 0, and minus 2 C1 minus C2 plus C3 is equal to 0. Now notice what I was doing, maybe not have explained this well. I was doing each term. C1 times 1 is 1C1, C plus C2 times 2 is 2C2 plus 0 times C3. The constants have to be 0. For the x term, C1 plus 2C2 plus C3, I'm sorry, plus 5C2 plus C3 is equal to 0. And for the quadratic terms, minus 2C1 minus C2 plus C3 is equal to 0. Okay. Here we have a matrix again, don't we? Okay. Let's see what we get. 1, 2, 0. I'm going to leave off those zeros. You know they're going to stay. 1, 5, 1, and minus 2, minus 1, 1. Now, let's just see what we've got. Here are our coefficients of the first one, right there. Here's the coefficients of the second one, right there. And there's the coefficients of the third one. Let's do our row reduction and see what we get. Unless you'd rather do a determinant, that would be good too, but it just depends on what floats your boat. Minus row 1 plus row 2 is going to be the new row 2. Let's see what that produces. Using row 1, 1, 2, 0, that would be a 0, 3, 1. Down here we'll do 2 row 1 plus row 3. That's a new row 3. My goodness, I am rapidly running out of energy. I think it's hunger, but hold on just a minute. Sugar is just empty calories, so I'm hoping that'll be enough to get me through an hour. I had a few almonds between classes, but I didn't have time for much, so that ran out a while ago. Okay. So 2 times row 1 plus row 3. So that'll be a 0. That I think will be a 3, won't it? And that's a 1. Guess what, team? If I did that right, what do you see? These are linearly dependent. I wrote too many things in there. Dependent, okay? I think that's what it was asking, wasn't it? Determine whether the set of vectors R2 is linearly independent or dependent. Dependent. And why? Because you'd wind up with a row of zeros there. Next step. Okay? Now, if you carried that out, and I don't know how they did theirs. Oh yeah, they're going to divide everything by 3. But you don't have to do that. You could have said 0 times row 1 plus 1 times row 2 plus, or polynomial 2, minus 1 times row 3 will work. Let's see if that works. Let's just do, no, I don't see that works. Oh no, that's right, sorry. I was jumping the gun. You'd have to go and do your row reduction, which sort of stinks. Actually, let's just do this. The next step, if we were doing that, we just subtract row 3 from row 1. I mean row 2 from row 3 or whatever. 1, 2, 0, 0. We're going to start with 3, 0, 1, 0, 0, 0. And then, this isn't the way we usually do it, then let that become 1, 2, 0. That, well, let's see. Let's go on and, yeah. I'm trying to do too many shortcuts. 0, 1, 1/3. Okay, and then this stays 0, 0, 0. I see no reason to do anything other than that. Okay. Then minus 2 row 2 plus row 1. Be 1, 0. Minus 2/3. And this will be a 0, 1, 1/3. And this, of course, is 0, 0, 0. Okay. Now, since you have no C3, make that some arbitrary, there it is. Let C3 equal T, say. Then C2 plus 1/3 T is equal to 0. So yuck! So C2 is equal to negative 1/3 T. And then C1 minus 2/3 T is 0. So C1 is equal to 2/3 T. And the easiest T for me would be to choose T equal 3. When T is equal to 3, C1 would be 2, C2 would be minus 1, and C3 would be 3. Is that the one they come up with in the book? Yeah. 2, negative 1, 3. Perfect. And that produces a 0. Not all those are zeros, linearly dependent. Does that make sense? All right. Let's go to example 10. If all you got that down, let's go to 10. Determine whether the set of vectors in M22, that's 2 by 2 matrices, is linearly independent or dependent. So here's the set that we have. S is equal to the set of 2 by 2 matrices. Okay. 2, 1, 0, 1. That's the first one. 3, 2, 3, 0, 2, 1. 1, 0, 2, 0. Okay, and these are our three vectors now in the general sense. Vector 1, vector 2, and vector 3. Okay. Now, just like before, oh man, we do C1 times this one plus C2. This is just so I don't have to write them several times, plus C3 times this one. If this would write this sorry thing, C3 here. Okay, so let's, and then of course that combination would need to be the 0 2 by 2 matrix, 0 vector in 2 by 2 matrix land, which is 0 0 0 0. So everything's a 0 again. Okay, so what do we have here? The first equation would be 2C1 plus 3C2 plus C3 plus C3 is equal to 0, because that whole matrix is 0. And it doesn't matter what order you do. C1, I'm doing this one now. C1 is equal to 0. That's this one plus this one plus this one. Okay. The next one is 0C1 plus 2C2 plus 2C3 is equal to 0. I'm sorry, I can't believe how dry. My throat is. Okay. And then the fourth equation is C1 plus C2 is equal to 0. All right. Now that C there is a pretty ugly one. Let me see if I can. Okay. This is so aggravating. This is nuts. Okay. Trying to get too fancy with it. I'm just going to draw. Okay. Now, here I want you to see the easy way to do this. All right. Obviously, from this equation, C1 is equal to 0. From this equation, C1 plus C2 is equal to 0. C1 is 0, so C2 is equal to 0. You see that? 0 plus C2 is equal to 0. Well, then if C2 is equal to 0, 2 times 0 plus 2 times C3 is equal to 0. That implies that C3 is equal to 0. Okay? And if C1 is, well, there you have it. The only linear combination of this that would produce the 0 vector would be all zeros. So this set of vectors, even though I never would have suspected it, is, where are you there, linearly what? Say again? All these are zeros. Independent. See if I ask you again, okay? All right. Let's see what the book said. You don't need Gaussian elimination to do it. Just think through it. It has a trivial solution, which means the set is S is linearly independent. All right. That was pretty easy. That one didn't look like it was going to be, but it was. Let's clear that and go to example 11. Okay, you're coming in awfully soft now. Wait. I think I see the problem. I think my speaker somehow got turned to 10%. Goodness gracious, who did that? My wife's been in here again, hasn't she? Okay, say something else. Oh my goodness, yes. Okay. Quit yelling at me. Okay, never mind. What were you saying?
So basically, we're using a system of equations to figure out if the set is independent or dependent.
Absolutely, that's it. If the only way you can get it is for all the C's to be 0, immediately it's independent. If you get parametric equations that you can plug in a number other than 0 and get some combination that has something other than 0, dependent. You're absolutely right. So let's do, these are just regular old vectors, but we'll treat them as if they're M41s. Okay, here's the set S, which is a set of these 4 vectors here, V1, V2, V3, and V4. Okay, and those 4 vectors are, that's supposed to be a brace I don't draw well. Okay, column matrices or column vectors. I call them column vectors. 1, 0, -1, 0, comma, 1. Yeah, get out of there. The comma disappeared. 1, 1, 0, 2. Three would be 0, 3, 1, -2. And the fourth of these vectors would be 0, 1, -1, 2. Okay. Yeah, that brace looks a lot better. Okay. Now, again, I'm going to keep from writing them again. I'm just going to say C1 times that one, plus C2 times that one, plus C3 times that one, plus C4 times that one. And what we want, can we make that equal, yeah, get out of there. Make that equal the 0 vector, which is 0, 0, 0, 0. So I'm just going to call it 0 vector. It's a 4x1 matrix. Okay. Again, this one's really easy to write down. That would be, I'm going to skip the C's in there. 1, 1, 0, 0. 0, 1, 3, 1. Negative 1, 0, 1 minus 1. See what I'm doing? 0, 2, negative 2, 2. Okay. I'm going to give you half a second to come up with what my first step is going to be. Maybe longer. I'm going to divide that bottom row by 2 and make it 1, negative 1, 1. Okay, is that okay? I probably should have been a little bit neater with it and use my eraser since they had it here, and get rid of the 2's there. Yuck! Okay, I got rid of the 2, all right. That was a 1. Okay, all we have to do is do this. How do you want to do it? Gauss Jordan's pretty easy. Let's do it. Row 1 plus row 3, all right? I was going to say it may not be hard to do a matrix here, but I mean a determinant here, but it's pretty easy doing this. All those zeros help in either case. 1, 1, 0, 0. The trouble is you have to write so many times here. 0, 1, 3, 1. 0, 1, 1, minus 1. Correct me if I'm wrong, okay? And 0, 1, minus 1, 1. Okay. Now, I'm really tempted, and I'll probably yield to temptation too, of adding these two rows together, okay, and that's going to eliminate, this will become a 2 and those are 0 and that's a 0, right? And then I'll divide by 1. I'm going to move that up to the second row, okay? It's all right to do that. That's really cheating, but it's all legal in most states. Add these two together, you get 2, 0, 2, 0, 0. Divide by 2, you get 0, 1, 0, 0. Okay, so I'll make this a 1, 1, 0, 0. Move that up here and make it a 0, 1, 0, 0. And then move the next one down, 0, 1, 3, 1. And this stays as 0, 1, minus 1, 1. I can't remember which one I did. Yeah, I think that's okay. Okay. Say again? Okay. Now, okay. Next, I want zeros above, where is my, there he is, okay. So minus row 2 plus row 1, okay. So that becomes a 1, a 0, a 0, and a 0. I like that one. 0, 1, 0, 0. I like that one. Now we'll do a minus row 2 plus row 3. Minus row 2 plus row 3. And that becomes a 0, 3, no, 0, 0, 3, 1. And this becomes, oh, let's do this one. Minus row 2 plus row 4. Okay, and that becomes a 0, 0, negative 1, 1. Okay, here's what I'm going to do next. I'm going to make that a plus and that a minus. Legal in most states. Okay, now I'm going to swap those two rows. Okay, because I like the first two just like they are. 1, 0, 0, 0, 0, 1, 0, 0. Swap these two. 0, 0, 1, minus 1, and 0, 0, 3, 1. I hope you're going to see things are going to come out fine, I think. This isn't long enough. Okay. Minus row 3, no, minus 3 row 3 plus row 4. All right. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, minus 1. And then finally 0, 0, 0, 4. Guess what? Divide that row by 4 and make it a 1, and then eliminate that one. It doesn't matter. The only way you're going to get this is for every one of those to be 0. Right? Okay. So that's linearly independent, at least in my mind. Use Gauss elimination, show the system has only the trivial solution, which means the set is linearly independent. Okay. Now, they have a little bit of verbiage here, so let me pause and talk the verbiage first. If a set, this is middle of page 182, if a set of vectors is linearly dependent, then by definition the equation has a non-trivial solution for which not all the c's are 0. For instance, if C1 is not equal to 0, then you can solve this equation for V1 and write V1 as a linear combination of the other vectors V2 through 3 VK. This is what we were doing before. I was almost surprised they took this long to get around to saying it. I didn't close off my bracket here. That bothered me. Okay. In other words, vector 1 depends on the other vectors in the set. That is a property characteristic of a linearly dependent set. Any one vector depends on all the rest of them, or one vector will depend on at least some of the others. Okay? And there is a little, oh wait, I'm sorry. That leads to theorem 4.8. I guess I'll write this out. I'll have to do it by hand. All right, clear? Sounds like an ER story. Clear? Okay. Oh, let me get it back in my lap. This is sort of awkward writing, but we'll do it. Okay. A set S, good old favorite set S, vector v1, remember that doesn't have to be a traditional vector, any old vector, vector v2, vector v3, dot, 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 up to and including vector v sub k. I assume they're still going to... Okay, there's a set of vectors. Now this is true for as long as the k is greater than or equal to 2. In other words, it's got to be a 2 by 2. I mean, you got to have at least 2 vectors in it. If you only have one vector, it's not going to be linear. That's linear independent automatically. If that vector is not the 0 vector, then that's a... Okay, so we're not dealing with just a single vector in a space, okay? We're going to have at least 2, okay? This set is linearly independent sorry, I'm going to have to go to writing like this so the pen won't mess up. That's if and only if. I mean, one points one way, one points the other way. At least one of the vectors at least one of those vectors this is so aggravating. At least one of those vectors v sub I, I'll call it v sub I, can be written as a linear combination of the other vectors. In S. Okay. Now, we've already been seeing that all along, and of course that would be true. The proof is basically there is some C, at least one C that's not equal to 0. Okay? Pick that vector that has that C in it. Okay, and write out the thing that C1 V1 plus C2 Z2 plus C3, you know, write all that out is equal to 0, and one of those C's is not 0. Okay, so pick that vector out, subtract all the rest of them away, and then divide by that C, and guess what? You get that vector I is a linear combination of all the other vectors. Okay, and that's basically what they're doing in their proof. So let's do example 12. I'm going to clear this. I may or may not need it, but let's see. In example 9, if you remember that, your set of vector S was, remember that's the polynomial ones, okay? 1 plus S x minus 2x squared (2 plus 5x minus x squared x plus x squared. Okay. We showed before, and by the way, they're naming this one as they did before, vector 1, vector 2, and vector 3. Okay. We know it's linearly dependent. We already did it. Show that one of the vectors in this set can be written as a linear combination of the other two. Okay? Now, back in example 9, we'll turn back and look at it because I've already erased it. We showed that, for instance, C1 equal 2, C2 equal -1, and C3 equal 3. That was the one we chose, and that's the one the book chose. That, not all the C's, in fact, none of those C's are equal to 0. Okay? So, what I would say then is I would take this vector, because we know that C1, or let me write it this way, 2V1, that's what I was trying to say, 2V1 minus V2 plus 3V3 is equal to 0. That's what this thing is telling us. With those choices here, you'll get the 0 vector. Okay? So that means we can move this to the other side and say V2 is equal to 2V1 plus 3V3. Let's see if that works. 2 times V1, that would be 2 plus 2x minus 4x. Let's write it out. 2 plus 2x minus 4x squared plus 3. Yeah, okay, sorry. That's not working. Oh, yeah, it is. Okay, so plus 3x plus 3x squared. Okay. What does that equal? 2 plus 5x minus x squared. There it is. That's V2. It's a linear combination of V1 and V3 with those coefficients. I think that's all they were asking you to do. Okay? Oh, I'm on the wrong page. Yeah, we have V2 is equal to 2V1 plus 3V3, and that is a linear combination of the other two. Now, theorem 4.8 has a practical corollary that provides a simple test for determining whether two vectors are linearly dependent. In exercise 77, you're asked to prove that corollary. So here's the corollary to theorem 4.8. We did theorem 4.8 before. Let's do the corollary here. I can't remember if I wrote it out. Seems like I did. Here's the corollary. Two vectors, two vectors I should be writing U and V in a vector space yuck V are linearly dependent if and only if, this is far easier than writing all that out, one is a scalar multiple of the other. Yuck. Okay. Now, we saw that already, okay, several times, I think, that if one is a scalar multiple of the other, hey, just multiply the one by the negative of that multiple, and you got the second one, and they add to 0, okay? So that's a pretty easy thing to do. And it's the 0 vector is always a scalar multiple of any other vector, okay? So therefore a 0 vector in a space is going to make it not a spanning set. We saw that before too. So let's do example 13. I don't think I need to clear it, but I will. Okay. I'm going to have to get me this is I just can't believe I get this dry this quickly. Okay. That was the last of my Coke, the last of my water, the last of everything. Hopefully I can make it, what, 20 more minutes. Okay. Example 13. 3 parts. A set S is equal to set of these two vectors v1 and v2. These two vectors are ordered triplets 1, 2, 0 and -2, 2, 1. Okay, now guess what? You don't have to set up and do a C1 times 1 plus a C2 times the other and do anything, because you've only got 2 of them. The only way, remember the other one was if and only if. Neither of these is a multiple of the other, right? So therefore, which? Linearly, finish it for me. You got it. Independent. Perfect. Okay. So let's do the B one. That was A. Here's B. Here's a set S equal V1 and V2. Why do I write this again? And now they're equal to the set of 4, -4, -2. Comma, -2, 1, -2, 2, 1. What you think?
It's a multiple.
Yep, multiple. Multiply the first one times -2, you got the second one. Or multiply the first one by the multiply the second one by -2, you got the first one. Or multiply the first one by -1/2, and you got the second one. Okay, either way. So this is linearly. I'm going to leave off the linear dependent. I'm just going to abbreviate it that way. Now, here is the third one. Oh, no, no, no. There is no third one. Those are the drawings for the other two. They go off in different directions, so they can't possibly be linearly independent. The other two head off in the same direction, maybe opposite directions, but along the same line. They are linearly, same line, linearly dependent. And believe it or not, we finished 4.4. Homework exercises here. Don't worry about sending any of these in to me. Get me your test. Get me your final. Get me your research paper. That's all I want for the rest of the term. Don't be sending in me any more homework. I don't need it. Just send me your product. Okay. Any of the odds, either 1 or 3. They're both at Calc Chat. They're both also in the back of the book. Either 5 or 7, both at Calc Chat. Any of the odds 9 through 17, all at Calc Chat. Any of the odds 19 through 25, all at Calc Chat. I'm sorry, 24, 23, all at Calc Chat. Do 25, it should be at Calc Chat. Any of the odds 27 to 39, they should all be at Calc Chat. Any of the odds 41 to 47, they should all be at Calc Chat. Either 49 or 51 should both be at Calc Chat. Either 53 or 55 should both be at Calc Chat. Either 57, well, do 57, it should be at Calc Chat. You can do 59 if you would like. It should be at Calc Chat. I didn't know my dog came back up. Okay. 61 should be at Calc Chat. 63s are true false. It should be at Calc Chat. It has 2 pieces to it. 65 is a proof. If you want to do that, you could do it as well. Well, in fact, 65 through 73 are all proofs. In fact, the odds 65 through 77 are all proofs. You can do as many or as few of those as you would like. If any of you are math majors, probably a good idea to do some proofs. If you're engineering majors, I don't know that many engineering majors really want to do that many mathematical proofs. So that's up to you. So let's see if we can get at least started in basis and dimension, 4.5. Okay. I think just for the purpose, we'll clear the screen. All right. Now, this is pulling in 2 parts of what we did before, maybe more than 2. Now, remember we were talking about spanning sets, and then all of a sudden quit talking about spanning sets and started talking about independence and dependence, right? And you may have thought, I meant to say it at the time, this seems a little strange. They're talking about one thing, then all of a sudden talk about something else, not tying them together. This section ties them together. In this section, you'll continue your study of spanning sets, so we pick those up. In particular, you will look at spanning sets as in a vector space that are both linearly independent and span the entire space. That's what we're interested in. Okay? They can, if it's a spanning set, it spans some space, but if it spans the entire set and they're linearly independent, then that's what we're looking at. Such a set forms a basis for the vector space. Now, if you remember back what we were talking about before with spanning set, the smallest number of sets, that will span whatever the smallest number of vectors that will, some linear combination of them will make up every vector in that space, okay, in that set, okay. Now we're saying if those span an entire vector space, we call that the basis, or a basis for that set. The smallest number of vectors that will define every other vector, some linear combination will define every other vector in the space. So here's the definition of a basis. We sort of said it. Here's a little more formally. Okay? A set of vectors, S, I'm going to leave off some of the work. Oh, why did that disappear? Okay. A set of vectors S, that's a set, just like we start just by every one of these, V1, V2, V3, dot, 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 up to V sub k is what we've been using. Is that what they're still using? No! I knew they were going to do it to me sometime. For some reason, they'll suddenly turn around and change your subscript. This is K. I think I know why. They're going to make this N this time. In a vector space, just like we've done before, vector space, capital V, is a basis I'm going to underline that. A basis, they bold it in the book, for V quit. For V when these conditions are true. Okay, that's supposed to be a colon, it's not. Number 1. I'll make that a colon here and make that number 1. Okay? S must span V. In other words, that set of vectors you have there, S, must, some linear combination of those vectors must be able to define every vector in V. Okay? That's 1. 2, second condition that must be met, S is linearly independent. Okay, that's supposed to be independent. It broke up my middle of writing and messed it up. Okay, so number 1, it must span. You must be able to create every vector in your vector space V from those vectors in S, and S must be linearly independent. In other words, you don't have any vectors in there that depend on one another. Okay, they must all stand by themselves. Okay, now a couple of other words here. If a vector space V has a basis with a finite number of vectors, then V is called finite dimensional. Otherwise, it's finite infinite dimensional. Okay? Now, what do we mean by that? Let's say the vector space P of all polynomials obviously is infinite dimensional, because you can't say, well, you can make it up of a finite number of vectors. No, you can't. You're going to need an infinite number. If P is all polynomials, N could go off into infinity. Now, the vector space of C of all continuous functions defined on the real number line from negative infinity to positive infinity. Infinite. You can keep coming up with more and more and more functions. Okay, the vector space that is made up of only the 0 vector, it only consists of the vector 0 is finite dimensional, obviously, only one. Many are in between those extremes. So let's do example 1 now. I think what I'll do is clear the screen here. Okay, if I can get, well, that's one reason it won't work. I'm rubbing on the wrong palette. Okay. Now, here's a pretty simple one. Here's a set S, and it's a set made up of these three very unusual looking vectors. 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay? That, I'm just going to write it down, is a basis for R3. Okay, now this is almost so simple it is mind-boggling to think you have to prove it. Pick any old vector in R3, v1, v2, v3, okay? Those are the components. Any components, okay? Now, v1 times that first vector there, plus v2 times the second vector there, plus v3 times the third vector there, that's going to define it. So any vector you have there, you can come up with a linear combination of these vectors to make it. So there's the first thing. It spans the set. There is no vector in R3 that cannot be made up of those three vectors. That spans the entire set. Number two, are these linearly independent? Of course they are. If you did these out in a matrix, you would have the identity matrix, which of course is invertible. It is the prime invertible matrix. Okay, so sure enough, that's a basis. Not only is it a basis, it is that's supposed to be the standard basis. That's the standard basis for R3. That is the basis that you build everything on. Is that the only basis for R3? No, by no means. Okay? For instance, 2, 0, 0, 0, negative pi 0, 0, 0, 15 thirds. That's also a basis. It's not standard, but it is a basis because you can multiply some combination of those three vectors to form any vector you want to in R3. Okay, but that's the standard basis. And not only that, for Rn, the standard basis would be 1, 0, 0, dot, 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 0, as long as you have n zeros here. Oh no, n minus 1 zeros. You have a total of n characters. 0, 1, 0, 0, dot, 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 up to and including 0. And you again have n. This is all n elements. 0, 0, 1, 0, 0, dot, 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 0, all the way up to dot, 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 0, 0, 0, dot, 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 until the last one is only 1. Okay. That would be your standard basis for Rn. N elements, and every one of them contains a single 1 in alternating positions, so they count them all. Okay. And we usually call those, I forgot they call this, even though this looks like something we used before, that would be E1, E2, E3, and this would be E sub n, I think is what they were using here. Yeah, for Rn, of course. Right. All right. We've got 6 minutes left. I don't think I'll be able to get example 2 done in a single minute, so I think we're going to have to stop. Okay? And the reason I'm stopping is let's go see if I can find it. There it is. There it is. Here is the test. Now I'm going to move James. He's always in the way, isn't he? Okay. All right, move him aside here. Okay. Now, it says test 3, that's test 4. Sorry. Okay. You can do number 1. Okay. You can do number 2. You can do number 3. You can do number 4. Okay. Now that's P8. Remember what that is? The set of all polynomials of degree 8 or less. Okay. You might need more room on some of these things, but you got it. I mean, okay. You can do number 5. We did that. Okay.
Could you repeat that again?
Repeat what again?
You said not to do what number?
Okay, I haven't said not to do any numbers yet. All of them you can do so far. Number 1, 2, 3, 4, 5, and 6 are similar. Wait, I'm sorry. Yeah. Determine whether W is a subspace. You can do number 5. You can do number 6. Same direction here goes for this one and that one. Okay. 2 different problems. Okay. Number 7. Here is a set. Okay. Determine whether it spans R3. Whether it's linearly independent, and whether it is a basis. So you can do number 7. We got enough done in 4.5 for you to do that. So you can do number 7. You can do number 8. Okay, we didn't do any with matrices, but we did them for others, so you can do that, number 8. And that's basically yes or no, okay? Now, number 9, we did not do. We ran out of time before we got that far. So number 9 is completely optional. You can leave it blank. It doesn't count against you. You can guess. A wrong answer doesn't count against you. A right answer could give you a bonus point. So if you want to read ahead, look up and see if you can figure it out, you can certainly do that, but it's not required. 1 through 8 is required. Now, if you finish this test Sunday morning and you haven't done number 9 and you're wanting to spend a few hours trying to figure out number 9, don't get me the test, okay? Don't waste time. If you finish it this afternoon and want to figure out whether number 9, you can do that for extra bonus points. I don't care. That won't bother me at all. But don't be turning it in late just trying to get number 9 done. So everybody does 1 through 8. You can all leave number 9 blank. You can all guess. You can all try. It will not count against you if you miss it or leave it blank. It will be bonus if you get it right. It's not going to be a lot of bonus. Don't waste a lot of time on it, but I will give you at least a bonus point or two. Okay? Any questions? So 1 through 8, do. 9, optional. Completely optional. Okay.
Where it says describe the zero vector, it's just saying describe the zero vector in general, just any zero vector.
No, in that space we talked about, number 4 right here. Describe the zero vector and the additive inverse of a vector in the vector space P8.
Okay, so describe the zero vector of P8.
Yeah, exactly. That's it. Yeah, and then if you come up with a vector in P8, then now make it a generic vector in P8. Okay. In other words, have just letters representing coefficients or something like that. Yeah. Okay. But for the zero vector, you'll have numbers representing the coefficients. I think you know what numbers that will be. Okay. All right. Good deal. Good question. Any others? All right. Now, one more thing, and I think I mentioned this before, but in case I didn't, just this week, they have opened the student course evaluations. I've got all of you here. I hope all of you are listening. Please do your student course evaluations. We value those things. They're beneficial for me as an instructor, for me as a department chair, for the deans, for everybody. They're very helpful for us. It helps me become a better teacher. It helps us see where weaknesses are, things we can work on. So please do your student course evaluations. It doesn't take long to do. Has anyone already done it?
Yes, sir.
You have. How long did it take? Okay. I've heard anywhere from 5 to 15 minutes. So if you really take your time, it could be a little longer, but most of the time you can knock it out really easily. Please do the student course evaluations. Now, for those of you who haven't done them yet, look at your Lawson State email. Once you find that, scroll back until you see an email coming in this week from the dean, Dr. Cherie Davis probably. And if you find that thing and it talks about student course evaluations, look for a link. Somewhere in that email will be a link. All you do is click on the link, you're there. The directions for how you log in and your password, all that are there. So please, folks, do your student course evaluations. Thank you, the two of you who said you had done it already. Excellent. Thank you. All right. Any other questions, comments, problems, issues? I've really enjoyed this class. We got almost as much done as I've ever gotten done in a linear algebra class just because y'all were so good at it and you participated, even though this term turned out being about a week and a half to 2 weeks short, okay, of what it should have been. We still got a lot done. Not as much as we could have done, and I apologize if this does cost you in your later thing. I have a feeling most of what you need from linear algebra you've been exposed to now. So it's been great having you. Get me your work, okay? Show me the money. Show me your work. Any last thoughts? Parting shots? Yeah.
Did you ever finish grading test 2 and test 3?
Say that one more time.
Were you ever able to finish grading test 2 and test 3?
Was I ever able to send you the grades? Is that what you said?
Grade test 2 and test 3.
Okay. I'll have to look in my grade book. I think it's in this pile. You may not have been in here at the beginning. Not all this, but the vast majority of this came in this weekend. So I have spent almost the entire week printing tests and almost no time grading tests. Let's see. No, I have not gotten test 2 or 3 graded. Everything that's been sent to me before sometime yesterday has been printed, but I don't have them graded yet. They are here in the stack, And I started grading last evening when I finally finished all the printing, and I will continue grading this afternoon. I have one appointment for a advising session, and except for that, I plan to be grading the rest of the afternoon. I have a class starting at 5. It goes till 6:30. So except for that time and my 30-minute advising, I'm going to eat lunch sometime. So there goes most of the afternoon. But no, in there I will be grading, grading, grading. So now it'll be a while before I get it on Blackboard yet, but I will be getting things graded. From just looking at what has been turned in, everything looks pretty good. I can't say anything more than that, but it looked good. All right, sorry I don't have those finished grading yet. But like I said, just about every spare moment that I've had, I've been printing tests, printing product rather than grading product, because so much has come in. That much has come in since the weekend. I had maybe a very thin stack, but I've got most of those graded. Well, not those. I've got things graded equivalent to that, but I've just been putting them in order so I can get to them and knock them out. So sorry, no. I've been printing, printing, printing. Hopefully now I'll be grading, grading, grading. All right, any other questions, issues, concerns? All right, take care. Stay safe. Numbers are still increasing like crazy. In fact, in one of my other classes, one of my students had to quit coming because the doctor feels like she could have COVID or she could have a type of meningitis. And both of those are, neither one of those are good things to have. It's not, in fact, a lot of meningitis is being caused by COVID. So either she's already had it and didn't realize it, and now she's got a secondary, or else she has the primary. Stay safe, people. Don't be tempted to not be safe. Take care of yourselves. Good luck to you going back to your home campuses, and I know Jemanuel will be back in the fall, or at least he indicated that. James, you're finishing this summer?
Yes, sir.
Okay, good luck wherever you're heading. You may not be heading anywhere. You may be virtualing again. So whatever is up, hang tight with it. Do well. Proud of you. Take care. Bye-bye. Enjoyed having you.